Hello guys, welcome to Electrochemistry. Okay, this is another session where we will be discussing about conductivity and molar conductivity and how they vary with concentration. We will be also looking into strong electrolytes and weak electrolytes. So let's begin. So here, if we talk about conductivity, conductivity is the one which always decreases with decrease in concentration. Okay, so it is for the case of both weak and strong electrolytes. We will discuss what is weak and what is strong electrolyte. Now, why this is happening? This is happening because the number of ions, okay, per unit volume that carry the current in the solution decreases on dilution. Okay, so basically when you decrease the concentration, ions are the ones which are actually providing conductivity. So if you decrease the number of ions per unit volume, you are decreasing the conductivity. Okay, so hence conductivity always decreases with decrease in concentration for both weak and strong electrolyte. Okay. Now, the conductivity of a solution at any given concentration is the conductance of 1 unit volume. So here the volume is 1 unit of the solution which is kept between two platinum electrode with unit area of cross section A and at a distance of unit length. So if you want to write it down, you can write conductance G is equals to kappa A upon L. Okay, where A is the cross sectional area, L is the distance among the two electrodes. So if you see here, the unit cross section area is there and a unit distance is there. So both the values are 1 1. Hence conductance is equals to K kappa, that is conductivity. Okay, so conductivity of a solution at a given concentration is basically conductance, okay, of all these things. Conditions apply. Okay, that's why here G is equals to kappa. Now when we talk about molar conductivity of a solution, so molar conductivity at any given concentration is again conductance of volume V of the solution containing 1 mole of electrolyte. So here there is 1 mole of electrolyte which is kept between two electrodes with the area of cross section A. Here the area of cross section is not 1 unit. The 1 unit here is 1 mole of electrolyte is 1. Okay, and the distance of unit length, the distance L should be 1 unit length. So if you see here, the molar conductivity is basically kappa A upon L. L is 1 and area is basically equals to V because it is the volume which contains 1 mole of electrolyte. Okay, so this entire quantity simply becomes kappa times V volume. Okay, so this is your molar conductivity. Now when we talk about molar conductivity and when we try to decrease the concentration, okay, now understand that decreasing concentration simply means volume is increasing. Okay, basically you are diluting the solution. Okay, so as we know, conductivity decreases with decrease in concentration. So kappa is decreasing with decrease in concentration, whereas volume V is increasing. Okay, so you can see molar conductivity value increases with decrease in concentration. This is the overall result. Now what is happening? Because the total volume V of the solution containing 1 mole of electrolyte increases. Okay, so there are two factors which are taking place. One is kappa decreasing and the other is volume V increasing. Okay, so if you do the experiment, we note that lambda m value, or that is molar conductivity value, increases with decrease in concentration. Okay, so decrease in kappa on dilution of a solution is more than compensated by increase in its volume. Okay, so that is basically volume increasing is basically compensating the decrease in value of kappa. Okay, now if you look at the physical meaning, what is happening, that at a given concentration lambda m, it can be defined as the conductance of electrolytic solution kept between electrodes of a conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of electrolyte. So please note here there is 1 mole of electrolyte and the distance is 1 unit. Okay, that's why the A by L part became V. Now there is one thing that is much more interesting here, like for example when the concentration approaches 0. when concentration approaches zero, the conductivity value or molar conductivity value is known as limiting molar conductivity. This is also known as on infinite dilution. Okay. When we talk about limiting molar conductivity, we represent it by lambda m naught, okay, or E double dot on the top, m naught. Okay. Now let's see the scenario of strong and weak electrolyte. Now here this is a graph which is representing KCl and CH3COOH, which is acetic acid. So this is lambda m versus C raised to half. Please note this is not just C, this is C raised to half. So what we notice is for the case of CH3COOH acetic acid, when you decrease the concentration, the molar conductivity value increases rapidly, especially at infinite dilution. Okay. Same way, if we talk about KCl, it is also increasing, but it is increasing steadily. Now, here, this is the case of strong electrolyte, KCl. Now, meaning of strong electrolyte is basically the ones when you put in water, they dissociate completely. So, KCl dissociates completely as K plus and Cl minus ion. Whereas, CH3COH is not dissociating completely. It has some degree of dissociation, which we will see now. Okay. So let us try to see KCl or strong electrolytes in more detail. So when we talk about strong electrolyte, we notice that lambda increases slowly with dilution. Okay, so as you are diluting, you are lowering the concentration. You see the value of lambda is increasing or molar conductivity is increasing. Okay, so since this is kind of a straight line, we can represent it with y is equals to mx plus c. Okay, so this here is limiting molar conductivity, so at infinite dilution. Now here the value of a, that is the slope of this equation. Okay, you can see this constant a for a given solvent and temperature depends on the type of electrolyte. Okay, now type of electrolyte meaning the charges on the cation and anion produced on the dissociation of electrolyte in the solution. Okay, let's talk about these charges. Let's say NaCl is there, so NaCl is having +1 and -1 charge. You can see +1 -1. CaCl2 is having +2 -1 charge, so +2 1 charge, so 2 1. MgSO4 is Mg2 plus SO4 2 minus, so 2 minus 2, okay, or 2 2 electrolyte. So these are the different types of electrolytes. Okay, so the value of A depends on how many charges are there on cation and anion respectively. Okay, now in order to calculate the value of limiting molar conductivity, we have Kohlraasch law of independent migration of ions. Now, what does this law tell us? It simply tells us that limiting molar conductivity is actually the sum of conductivity due to cations and due to anions. Now, let's take an example where not lambda, nu plus cations are produced and nu minus anions are produced. Okay, each cation is having lambda plus naught limiting molar conductivity, and each anion is having lambda minus naught value of limiting molar conductivity. So the total conductivity will be given by lambda m naught or E m naught is equals to number of cations into conductivity of individual cation plus number of anion into conductivity of individual anions. Okay, so this is your final limiting molar conductivity. Now this is at infinite dilution. Okay, so here is some values of conductivity values, that is lambda naught values. You can see H plus, Na plus, K plus, Ca2 plus. So all these are values. You do not have to memorize. These will be given in your numericals. Okay, this is an exam question. So this was about strong electrolytes. Now, when we talk about weak electrolytes, for example, we have acetic acid, CH3COOH. So they have lower degree of dissociation at higher concentration. Meaning is they do not dissociate completely when the concentration is high. Okay. So when the concentration is very high, they are not dissociating completely. But when you dilute, okay, when you dilute them, they are having a lot of free space. Hence, their degree of dissociation also increases. Okay, so hence for such electrolytes, that is weak electrolyte, the change in lambda m with dilution is due to increase in degree of dissociation. So here the degree of dissociation is low, but at this position, at low concentration, the degree of dissociation is quite high. Okay, so in such cases we see that em naught values or em values increases steeply on dilution, especially near low concentration. That's why you see that there is a very huge amount of increase in lambda m values. Okay, at infinite dilution, if I talk about infinite dilution, that means concentration is approaching towards zero. Okay, in this case electrolyte dissociates completely, so the degree of dissociation, which is alpha, is actually equals to 1. Okay, but at such low concentration the conductivity of the solution is so low that it cannot be measured accurately. Okay, that's why we see that this graph is not giving any value in y-axis. Okay, now if we know that alpha is the degree of dissociation, then it can be approximated to the ratio of molar conductivity, that is em values at concentration C, to limiting molar conductivity values em naught. Okay, how to relate that? Simply alpha is equals to lambda m upon lambda m naught. Okay, so this is the degree of dissociation alpha. Now if we talk about dissociation constant of an, let's say, acid, okay, because this is CH3COH is an acid, so we can calculate the value of Ka. So it comes out to be C alpha square upon 1 minus alpha. It's very easy. You can always do this like from the 11th standard. So you can write down the reaction CH3COOH gives you CH3COO minus plus H plus. If you write down that, and let's say initially the concentration is C and alpha is the degree of dissociation. So at equilibrium or at this value Ka, like after dissociation, the concentration remaining of CH3COH will be C into 1 minus alpha, whereas the ions which will be formed, their concentration will be C alpha and C alpha respectively. So when you put the value of Ka, that will become C square alpha square upon C bracket 1 minus alpha. This one C and another C square gets cancelled, hence you get C alpha square upon 1 minus alpha. Now here you can put the value of alpha as lambda m upon lambda m naught. When you do that, you get a relation between Ka and limiting molar conductivity values. Okay, that's it guys. Okay, I hope you enjoyed it. Let's see in the next session. Bye bye.